Dear colleagues, I am pleased to present a scientific report on the topic detection and recognition of mines using magnetic field sensor and Kolmogorov-Arnold networks. The author of this paper are displayed on current slide. Agenda. The structure of today's presentation is as follows: motivation, changes and improvements, references and related works, goal and tasks, neural network morphology, computer experiment, summary and conclusions. Motivation. Our research was driven by the need to develop the alternative mine classification model that suppresses the limitation of traditional convolutional neural network (CNN). To address these challenges, we propose to use of Kolmogorov-Arnold networks (CAN), which offer unique advantages in both interpretability and robustness. One of the key improvements introduced by CAN lies in its interpretability. The integration of spline-based weight functions allow for precise analysis of the influence of individual input features. Another major advantage is robustness. Our experiments demonstrate that CAN models exhibit stable convergence behavior without sharp fluctuations in the loss functions, even when trained on datasets enriched with noise. This ensures the reliability of the model under real-world sensor conditions. The combination of interpretable spline weights, sensitivity to subtle anomalies, and scalability potential makes CAN a compelling foundation for the next generation of modular passive mine detection systems. Specifics and approach. Traditional mine of detection techniques, particularly those based on active sensing technologies, carry a significant operational risks. Active detectors may emit signals that inadvertently trigger explosive devices, placing both operators and surrounding civilians in immediate danger. This really highlights the critical need for safer alternatives in mine detection. One such approach is the passive detection, which relies on the measurements of magnetic field anomalies rather than emission of probing signals. By avoiding direct interaction with buried explosives, passive methods dramatically reduce the likelihood of accidental detonations. In this context, our work focuses on enhancing passive detection capabilities through the use of Kolmogorov-Arnold networks, which are particularly well suited for identifying subtle anomalies in magnetic signatures. Related works. Our research builds on extant prior work, including influence of symmetry, neural network morphology of the mine detection metric. The authors investigate how the symmetry in neural networks morphology affects mine detection metrics. Yemas et al. Passive mine detection and classification method based on hybrid model. This paper introduced a passive mine detection approach using a hybrid model. The method demonstrates the potential of passive systems in accurately classifying various mine types. Lytvyn et al. Development of a hybrid neural network model for mine detection using ultra-wideband radar data. This study presents a hybrid neural network architecture designed to recognize mines using ultra-wideband radar data. The model effectively filters reflected signals with interference, enhancing the accuracy of mine detection. Lytvyn et al. Passive methods for mine detection and classification using magnetic fields and convolutional neural networks. The study presents a passive detection method employing magnetic field and convolutional neural networks for detection. Liu et al. Kolmogorov-Arnold networks. The authors propose Kolmogorov-Arnold networks as an alternative to traditional multilayer perceptrons. CAN utilize learnable activation functions on edges, offering improved accuracy and interpretability in modeling complex functions. Vasyl et al. A survey of Kolmogorov-Arnold network. This comprehensive survey explores the theoretical foundation, applications, and future potential of CAN. Goal and tasks. The aim of this research is to design and optimize a Kolmogorov-Arnold network architecture capable of accurately classifying mines under various soil conditions. This includes fine-tuning the number of hidden layers, neuron space layer, and the properties of the spline basis function. This work is directly relevant to Ukraine post-war recovery and the broader global missions of humanitarian demining, where accurate and safe detection technologies are critically needed. B-spline explanation. To understand the unique structure and functionality of Kolmogorov-Arnold networks, it is essential to examine the mathematical foundation of B-splines, which constitute the core compositional elements of CAN functional layer. A B-spline is a piecewise defined polynomial function widely used in numerical analysis and computer graphics for modeling smooth curves and surfaces. It's defined over a non-decreasing sequence of control points and corresponding knot vector, which determines the location and continuity properties at the boundaries between polynomial segments known as knots. Each segment of the B-spline is a polynomial of the specified degrees, and the entire function is constructed to maintain a specified degree of smoothness, continuity, across adjacent segments. This property allows B-spline to represent complex smooth functions while maintaining localized controls. Mathematically, B-spline of degree k is expressed as a linear combination of basis function bik from x, each of which is recursively designed using the Cox-de-Boer recursive formula. This recursive construction ensures computational stability and adaptability. One of the key advantages of B-splines is their lock and control property. Changes to a single control point affect the shape of the curve only in a limited region. This makes B-splines particularly effective for geometric modeling, smooth function approximation, and data interpolation, especially in scenarios involving noise or non-uniform distributions, precisely the challenges encountered in passive main detection using magnetic field anomaly. In context of CAN, the B-spline mechanism allows the network to flexibly learn smooth nonlinear mapping from sensor input and classification output, with a level of interpretability and regulation not typically achievable using conventional activation functions. Neural network morphology. The architecture of proposed Kolmogorov-Arnold network is designed to process magnetic anomaly data for the purpose of mine classification. The model receives a compact yet informative input vector consisting of three features: voltage, height, and soil type. These features are chosen for their relevance to magnetic signature variation and mine detection accuracy. The input layer Weight 3 maps these three features into the first hidden layer using spline-weighted connections. The network then propagates information through two fully connected hidden layers: layer 1, 3 times 16, layer 2, 16 times 16. Each layer utilizes spline activation functions denoted as phi, which allows for localized and interpretable nonlinear transformation. This spline function enables the network to approximate complex mapping while maintaining smoothness and avoiding overfitting. The output layer, which shapes 16 by 4, produces a probability distribution across 4 mine classes, providing interpretable and differentiable predictions for mine classification based on 3 input features. To enhance the model generalization and prevent overfitting on a limited dataset, a data preprocessing strategy was implemented. Specifically, we augmented the data by adding pseudo-random noise to the voltage and height values. This synthetic variation simulates realistic measurements, error, and environmental fluctuation, resulting in a more robust training process. The pseudo-random augmentation expanded the diversity of training examples while presenting the underlying structure of the data. Computer experiment. To evaluate the performance of proposed Kolmogorov-Arnold network architectures, we conducted a series of training experiments using two configurations: CAN 3.16.16.4 and CAN 3.64.64.4. The input vector combined three features: voltage, height, and soil type, and the model produced 4 output classes representing different mine types. The performance assessment employed a comprehensive set of metrics: accuracy, the ratio of correctly predicted instances to the total number of predictions; precision, the proportion of true positive predictions among all predicted positives; recall, the proportion of true positive captured among all actual positives; F1 score, the harmonic mean of the precision and recall. Macro and weighted averages provide class agnostic and class frequency weighted summaries, respectively. For CAN 3.16.16.4, the model achieved an overall accuracy of 93.56%. The training loss steadily decreased while the accuracy curve rose consistently, confirming the convergence of the model. The confusion matrix indicates minor misclassifications, particularly between classes 2 and 3, where overlapping magnetic characteristics may occur. In contrast, the deeper configuration CAN 36464-4 yielded an improved accuracy of 95.59% and macro averaged F1 score of 0.9556. The confusion matrix for this model demonstrates fewer errors across all classes, especially a significant improvement in the correct identification of class 2. Moreover, the loss function shows more rapid and stable convergence, indicating better learning dynamics in expanded architecture. Comparison of two architectures highlights the benefits of increased model capacity in handling more complex feature interactions. The CAN 36464-4 network not only reduced false positives and negatives, but also demonstrated improved generalization, particularly in classes that previously exhibit ambiguity. Summary and conclusions. To evaluate the performance of the proposed Kolmogorov-Arnold network architectures, we conducted a series of training experiments using two configurations, CAN 3.16.16.4 and CAN 3.64.64.4. The input vector comprised three features, voltage, height, and solid type, and the model produced four output classes representing different mine types. The performance assessment employed a comprehensive set of metrics: accuracy, precision, recall, F1 score, macro, and weighted averages. For CAN 3.16.16.4, the model achieved an overall accuracy of 93.56 with macro average precision, recall, and F1 scores of approximately 0.93. The training loss steadily decreased while the accuracy curve rose constantly, confirming the coverage of the convergence of the model. The confusion matrix indicates minor misclassification, particularly between classes 2 and 3, where overlapping magnetic characteristics may occur. In contrast to the deeper configuration, CAN 3.64.64.4 yielded an improved accuracy of 95.59%. The confusion matrix for this model demonstrated fewer errors across all classes, especially a significant improvement in the correct identification of class 2. Comparison of two architectures highlight the benefits of increased model capacity in handling more complex feature interactions. These results confirm the robustness, sensitivity, and scalability of CAN models for passive mine classification, with the larger architecture offering superior performance while maintaining smooth and stable training behavior. Thanks for your attention.